Welcome, this is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium. This conference would not have been possible without our sponsors, PQ Shield, SSL.com, Entrust, Keyfactor, HID Global, and the organizational support of the Post-Quantum Cryptography Working Group of the PKI Consortium, and in particular, Entrust, Keyfactor, and Logius. Would you like to join the PKI Consortium? Go to pkic.org/join, or contact us if you would like to become a sponsor.
Okay, next up, Yarkin Duraz, who will be talking about accelerated quantum supercomputing and post-quantum cryptography. Yarkin, from a co-founding startups to teaching at WPI, Yarkin Duraz brings entrepreneurial spirit to his role managing encryption libraries at NVIDIA. His expertise in post-quantum cryptography and fully homomorphic encryption helps keep NVIDIA's products at the cutting edge of security technology. Come on up.
Thank you. Thank you. Thank you for the introduction and this chance to give the talk. I'm from NVIDIA, and I'm going to talk about quantum computers. I know it might be a little bit funny for this week. So first of all, how many of you know we are actually also doing some work on quantum computers? Not many? Okay. All right. So actually, today I'm going to try to cover two sides of the coin. In one hand, quantum computers and its advancement. And then I'll discuss about post-quantum cryptography at NVIDIA and what we try to do and achieve to help and propagate the issue of quantum computers and its threats to cryptography. First of all, if you look at computing revolutions, we have a few of them. The first one is the scientific computing, and it helped the humanity to achieve certain advancements. After that, we can see we have deep learning, and then recently we can see that we have generative AI, which is the most recent computing revolution. And now another one is coming up, which is the quantum computing. NVIDIA, it's not building any exactly qubits, a quantum computer, but we are helping all the quantum computers to build their own accelerated quantum supercomputers. The accelerated quantum supercomputer, it's basically a hybrid computer where it has a traditional computer, accelerated computer part, and a quantum computer part. The logic behind is that quantum computers, they can do certain number of computations very well, but they cannot do all the computations. So at the end of the day, you need a hybrid computer to do and run algorithms. And a quantum supercomputer simply has a traditional part that runs a hybrid algorithm, and it runs its traditional part on the supercomputer, and it runs the quantum computer algorithm on the quantum computer. It's a software platform to actually help implement your own applications and distribute it in the between the workloads. Another important thing of this supercomputers that is needed for quantum computing is they need to be qubit agnostic, because right now there are no any standards. Every quantum computer have their own physical way to produce these qubits. So you need to support all the platforms until it gets a standard or achieves a standard. All right, quantum computing, it needs accelerated computing. Why? Well, with accelerated computing, we can run actually AI models on many things. And AI supercompute can help developing quantum computers and deploying quantum computers. For the deployment, it can help us on the quantum error correction side, creating more optimized hybrid algorithms and applications. And furthermore, it can help us for calibration, control, and readout. For the development, if you want to develop a quantum computer application, it can help you accelerate things when you are building it. Oops. One way to also look at it is the AI can assist you in the circuit design to accelerate the design of the quantum computer. And also, it can help you with dynamic simulations, noise modeling, and so on. At the end, what we want to achieve is accelerated quantum supercomputers so that we can run applications, right, very fast. But we are not there yet. We are simply trying to figure out the qubits, make them more stable, have less error on the qubits, and do more computation. So we are trying to increase the qubit size, right, all the companies. And in order to achieve this transition from qubits to the accelerated quantum supercomputers, AI can play a significant role to help to create better quantum hardware, more optimized hybrid algorithms, implementing better optimized and new quantum error corrections, and also help with infrastructure challenges. This is kind of a bit what I said, but the AI, it needs to run on, it needs a lot of computation power, so you need a supercomputing platform, and AI supercomputer can run and help you to accelerate quantum application development and quantum hardware development. But you can think this as a loop as well. Once we achieve a decent accelerated quantum computer, it can help us to accelerate AI. We can do better AI trains, better modeling, which can improve the AI. And it can circle back, and again, the AI can help us to make better quantum computers. So artificial intelligence, AI for quantum computing, it's kind of a new and emerging concept. There was a joint research with a lot of researchers and NVIDIA, and they write a paper on where AI can be used to help promote and accelerate quantum computing. And we can divide them into a few stages. The first one is the quantum computer hardware development and design. In a way, you can think this when you are writing or designing a hardware, like Verilog code, or when you are writing a software, like in C++, Python, and so on. Many tools, many LLM tools right now helping you. If you write a function name, it tries to print out a certain section of that code. Similarly, we can use the same technology, AI technology, to train and produce better hardware, to produce better quantum computer hardware. Another step, it can help us with processing, which means we can prepare the quantum circuits, like here it states what it needs to be. Rather than doing by hand, we can use the AI tool to help us and accelerate this process. During computation, doing some controls on the qubit, device characterization, device tuning, again, it can be controlled through AI tools. Another one, quantum error correction and decoding or code discovery. We can use AI to actually do these operations or find new codes. And as the last, when we take the output, we can use AI to do post-processing or help us with the post-processing, like mitigating the error, reading the qubit results, and basically doing the observation and evaluating. This is a joint work, and this is the first AI that is used for quantum computing. St. Jude's Children's Hospital and University of Toronto actually worked on this. So the whole logic is drug discovery applications, they can run on smaller quantum computers, but it suffers from optimization issues. Many of the computation and the circuit that you want to generate is parameterized, and it's hard to do the settings itself. So as a solution they came up with is kind of creating a LLM model for quantum circuit generation. So in ChatGPT, for instance, you type a few words, you feed it to the model, it prints out a sentence. Same way, you train a quantum model using operators, and then based on the operation you want, you describe it and feed it to the model, and it will print out your quantum circuit. By doing this, they are able to optimize certain classes of quantum algorithms, which has the quantum eigen solvers. And they achieve the limitations, or they avoid the limitations of the traditional variant quantum algorithms. So this is like a start of a new work, and we will see more and more of AI implications on quantum compute as well. Okay, so using AI, we are trying to also accelerate the creation of quantum computers. Of course, this kind of creates a challenge and a threat for the cryptography. Quantum computers, they run quantum algorithms using qubits, using the superposition and entanglement phenomena, which kind of accelerates certain algorithms. In our case, the threat comes from the Grover's algorithm and Shor's algorithm, which reduces the complexity of our hard problems in cryptography. So we need to urgently move to post-quantum crypto from traditional cryptography. And for that, NIST made an urgent call to standardize the NIST the urgent call to standardize these algorithms. Roughly, it started in 2016. Probably they were working on this much earlier. After a few runs, they came up with a few finalists, 1 key establishment and 3 digital signatures. Of course, this is not enough because all these new algorithms rely on new mathematical hard problems. These mathematical hard problems either very recently created, or even if it's out there, not many researchers worked on it previously. In order to make sure that we don't have any issues in the future, they are creating more rounds to add more algorithms for key establishment and digital signatures. Another thing from NIST, post-quantum crypto transition timeline, they want to disallow almost all the traditional crypto by 2035. So we have to make sure that we completely do the switch in roughly 10 years, which creates a challenge, especially given the infrastructure. Of course, when we are doing the transition, certain applications need to transition to post-quantum, and it might have performance effects. One of the important high-throughput applications for PQC, or even in traditional crypto, is the network. Many network servers, they do a lot of TLS handshakes, from 10,000, maybe tens of thousands to hundreds of thousands of TLS handshakes. And some of the standards, especially in the protocol level, since they are not set yet, and because we may need to use multiple digital signatures rather than a single one to make sure that we have safety if one of them is broken, The requirement kind of gets close to over maybe 500,000 to 1 million TLS handshakes per second. So in order to support these high throughputs, we kind of started looking into GPUs and wanted to see how much we can support high throughput transaction with GPUs by implementing a PQC library. We wanted to achieve a high performance and implement the standards. And I think one of the important things that we need to also have was the side channel security. We implemented MLCAM and MLDSA, and during the implementation, we realized we might have some certain advantages and certain disadvantages when we implement things on GPU. First of all, GPUs are very suitable for parallelization operations, so we were able to parallelize certain mathematical subroutines like number theoretic transform and so on. But on the higher level, GPUs are actually more suitable to parallelize, like you can batch maybe hundreds of thousands of MLCAM and MLDSA and execute them together. Another thing about GPU system, they have shared memory, and this shared memory is used between the cores, which help us to distribute the same problem into multiple cores, and they work together to solve it. Another thing, MLCAM, MLDSA, they are actually using a lot of registers inside the streamlining processors. And this causes the have a smaller or lower utilization on the GPU. So we rearranged the code to make some optimizations to have higher throughputs for MLCAM and MLDSA. Another limiting factor was CPU and GPU data transfers. It always costs some time. So you have to make sure that you minimize it. And also when you add batches of MLCAM and MLDSA transaction, it helps to reduce the total overtime. It amortizes it. One thing that we saw, this is an interesting result. Our security team looked into it. They looked into some side channel attacks that are applicable on CPUs and see if it's also applicable to GPUs. Well, since GPUs have massive parallelism, they actually do simultaneously a lot of cache and memory accesses, which cause a lot of power spikes in the system. And it causes a garbled power, EM, and memory traces in the system. So naturally, we create a noise inside the GPU, which makes it more resistant to side channel attacks. Only a small subset of known attacks are applying to the GPU threat model. And for that, we simply do randomization of the algorithm and added some masking data to countermeasure it. In terms of benchmarks, as I said, we need to batch them together so that we can have a higher performance and have an amortization for the transmission cost. Roughly, if you batch almost 1,000 of them, as you can see, if we increase the batch size, it increases linearly with the time. So we can amortize all the transmission costs after roughly 1,000 batches. And if we look at the exact numbers for keygen, encapsulation, and decapsulation, we achieve very high throughputs, roughly 20 to 10 million key generations per second for MLCAM. Encapsulation, again, we have similar range, 8 million to 20 million. And decapsulation, we have a similar number, 7.5 to 18 million. And we also compare it to a CPU implementation. In the CPU implementation, it's actually only on a single core. We don't use all the 16 cores. If we do execute a single one, it's slower than a CPU. However, if we batch them, execute 1,000,000 batches together, then we can achieve, depending on the security level, from 150 to 200 times speed up compared to a CPU. Encapsulation, we have a similar speed up again, roughly from 150 to 140. And decapsulation, again, we have a similar number, 140 and 130 times speed up. MLDSA, it's very similar, just the numbers slightly change. And one more thing, that MLDSA, it has different memory specs, and because of that, we cannot batch 1,000,000, but we can batch 100,000 signatures together and execute it. Again, roughly when we batch 100 to 1,000 of them together, we can get rid of the transmission cost and amortize it. With MLDSA, the numbers are slightly lower because it is slower. But for key generation, we can do 8 million, and on the highest security, it's 4.3 million per second. Signatures, usually 0.75, 0.57 million signatures per second, and for verification, it's 7 million and 3.5. In terms of speed up, in this one, we can achieve, for key generation, we can achieve more than 200 and up to 320 times speed up compared to a CPU. Signature, we can achieve slower or lower speed ups, roughly 50 times and 80 times. And for the signature verification, we can achieve roughly around 200 times speed up. Thank you. Questions?
Hi, everybody. Any questions from the audience?
I wanted to know quickly what is the state of this library? You know, if it's already finished implementing, and if you're already undergoing FIPS testing, and you know.
Right now, we are not doing the FIPS testing, but it's available. You can just download and use it.
Oh, it's open source.
Oh, well, it's free. It's not exact open source for IP issues, but it's an object file. It has an API. You can just go and download it and use it.
Thank you.
Go ahead.
You have shared your benchmark with your high-end H100. Are you doing some benchmark with your edge device, Jetson, or I mean the smaller device, more compact?
We haven't, but we are considering it. Do you have any need for that?
Yeah, I'm curious to know if you get the same. I mean, obviously proportional, but because those edge devices also have some limited capability. I'm not sure if it's a problem or not.
I heard that. I heard some applications actually that uses a lot of signatures, and it causes stress on the chip. So in the Jetson ones, actually.
Okay.
So we didn't have the time to expand into that yet, but I have that in mind, and if you have any specific thing that you are using for, we can discuss and do some tests.
Okay.
Definitely.
Yeah, I discuss that. Yeah. Thank you.
I'm wondering if NVIDIA has considered APUs to avoid the bottleneck from the PCIe lanes or are you just considering GPUs?
Versus, you said?
APUs, or perhaps systems on a chip where they incorporate the memory and the graphics all on the processor.
Right now, we just considered the GPU implementation. Depending on the use case and also demand, we can also consider them.
Okay. Yeah, that's something that always fascinated me, where from the bottleneck from the PCIe lanes, they removed that by incorporating it all on the processor.
Yeah.
So that might be a good use case.
Yeah.
Thank you.
Thank you.
Chris, anything from online? Okay, great. Any other questions? Okay, Yarkin,
All right.
thank you very
Thank you.
much.